Welcome. In today's video, we're going to be looking at the octahedron problem. So what is the octahedron problem? So this is a problem from one of Olympiad math paper this year, where you have a two-dimensional net of a three-dimensional shape. The three-dimensional shape is called an octahedron. It's basically 8 equilateral triangles put together. And a net is when you open up a three-dimensional shape and turn it into two-dimension as though it were a hollow shape. So what you see on the left is the net of the octahedron, which is basically the 8 equilateral triangle laid together, which when you fold, when you turn that two-dimension into a three-dimension, you get the octahedron. So the problem here is that you have a side marked Q, a triangle marked Q, and you need to determine the one that's marked as a question mark, which is essentially the face that's right next to Q. So how do you solve a problem like this? It might look very tedious, very cumbersome, and you might even be zapped a little bit saying, how do I translate a two-dimension into a three-dimension, and more specifically understand how to solve this problem of finding the face that's right next to Q. Now remember, whatever may be the problem, the fundamental skill that you need is fluid intelligence, which is to learn or know or identify the similarity between differences and differences between similarities. And I picked this specific problem because I wanted you to understand how the application of fluid intelligence will help you solve this problem. And even if it doesn't help you solve the problem, at least does it take you close enough. So first, let's begin by the fundamental, AB initio, the first point, the starting point of any fluid intelligence problem, which is observation. What do we observe in this net? We observe vertex, the corners, basically the vertices, the edges. When you connect two corners, two edges together, two corners connected by a line, that line is called an edge. And you have triangles. When three lines put together form closed space, that's called a triangle. So we have a bunch of triangles, a lot of edges, and many more vertices. So first, let's take this observation a little deeper. Let's analyze edges, for instance. A lot of edges, but there's a difference. Like, what's the difference between the red edge and the blue edge? You could say, yes, one is horizontal and one is probably oblique. That's absolutely right. But the way I'm looking at it, the dimension I'm looking at it is the red edge is connected only to one triangle, whereas the blue edge is common to two different triangles. In this case, the blue edge is common to both 3 and 4, whereas 1 is common only to 1. It's connected only to triangle 1. And therefore, this allows me to create many more red edges. So the ones that you see right now are all red edges connected to one triangle, namely 4, 5, and Q. It's also unique in that all of these red edges are horizontal. The next set of red edges are all horizontal inclined left. The next set of red edges are horizontal inclined right. So in total, you would have 4 horizontal, 4 oblique left, and 2 oblique right, making it 10 red edges. What about the blue edges? In total, you would have 5 which are oblique and 2 which are horizontal. So this is the analysis. Now, this hasn't solved the problem at all. We are far away from that, but we have understood the problem a little bit closer, a little bit deeper. Saying, okay, I see a lot of edges and some of those are red and some of them are blue. Classification is one of the fundamental technique with which you can apply your fluid intelligence to solve problems. Let's take it to corners. Now, all the corners that I've marked in blue have something similar. What is that? Can you pause and think about it? All the corners, the vertices that are marked in red have something similar. And everything that I've marked in gold has something similar. What is that similarity? It's a single dimension here. Can you think about it? Okay, if you have figured it out, fantastic. If not, it's the number of triangles that it's connected to, the number of lines that emanate from that particular corner. So the blue corners are the ones where there are only two lines emanating or they're connected only to a single triangle. The red corners are the ones connected to three triangles, and the gold corners are the one triangle connected to four different triangles. Okay, now let's analyze the triangles. Let's look at it from the perspective of triangles. I have colored four of them, 3, 5, 7, and Q. What's common between them? If you said its direction, it's absolutely right. All of these four triangles are looking up. The ones that's uncolored is looking down, it's pointing down. Let's take another dimension. I have marked these two triangles. What's common between them? What's similar between them? In this case, it's not direction because 3 is pointing up and 6 is pointing down. What is it? The answer is basically very similar. If you look at 4 and 5, they have something very similar in a different dimension, but they do not belong to the same set as 3 and 6. And the answer is connection. 3 is connected to 3 other triangles, 6 is connected to 3 other triangles. Whereas 4 is connected to just 2 other triangles, 3 and 4, and 5 is connected to 4 and 6. 1, 2, 7, and Q are all connected only to one other triangle. Let's take another one. I've already marked all the colors. Can you figure out what's similar between similar colored triangles? Like what's similar between 3 and 5, between 4 and 6, 7 and Q, 1 and 2? And the answer is adjacency, which means 1 and 2 can never be adjacent to each other. If you were to fold it along the corner that's common to them. Okay, you could somehow make it common by connecting one of the edges that is not there, but if you take the common point and you connect it out, then 1 and 2 will be opposite faces of an octahedron. 3 and 5 would be opposite faces of an octahedron. 6 and 4 would be opposite faces of an octahedron, and 7 and Q would have a similar relationship. But how does this help us? How does it get us to a point where we can solve it? And this is where now you can think of, when I fold it, finally one of the vertex is going to be one of the corners of the three-dimensional shape. So let's assume it's the gold that is connecting 2, 3, 4, 5 that's connecting here. Now ask yourself, which shape is going to be the golden triangle, right? And because it's unconnected to Q, it could be any one of them. Right? It could be any one of them which could be actually connected to 2, 3, 4, 5. We don't know what that is. But we know that the bottom 4 has to be 2, 3, 4, 5, which means what is left on the top has to be 1, 6, or 7. And you know that because Q is green, 7 is green, 7 has to be the opposite. And therefore, the side, the face that's marked as question mark could either be 1 or 6. We've at least narrowed down our answer into one of the two possibilities. There's another way to think about it. This time, let's connect the vertex of Q, because we know Q lies on that. So we'll connect the blue vertex there. Let's assume that the blue vertex is the corner that's connecting there, which means the two red vertices that is connected to Q also has to have something common with the side that is there. So now you can actually guess that the golden triangle that's marked beneath Q has to be 6. It has to be 6, and therefore the one that's opposite has to be 3. Why? Because 4, 5, 6, 7, which is all connected to the golden dot, have to be in the bottom face, and therefore 1 and 2 need to be opposite to each other, and therefore 3 could be this, which means now the answer could be 1 or 2. It gives you an idea, doesn't it? That in both the orientation, the common value is 1, so most likely I'll probably go with 1. However, it can be reoriented in different ways. Alright, so let's recap. The problem seemed impossible. We had a three-dimensional net and we were supposed to fold it into a three-dimensional shape, an octahedron. It's quite complicated. This is typically a problem for grade 7th, 8th, 9th, so it's definitely a tough problem to be solved. And many a times I've seen students just giving up. Oh, this is too hard, this is too difficult. But even a problem that's considered to be too hard or too difficult can be reduced in complexity if you were to use the methodology that I just taught you, which is to apply fluid intelligence, look for similarities between differences and differences between similarities, and then you will be able to form the connection that will help you solve the problem. So I hope you were able to enjoy the problem solving process, and it's something that you can apply in the problems that you will solve in your Olympiad exams. And if you would like to see many more such insightful videos, then please click on the like button and the subscribe button and click on the bell icon so you don't miss it out in the future. Thank you so much. Appreciate it.